Let's look at congruence in overlapping triangles. This could cause some problems for a lot of students. So let's say we have this triangle, for example, and we have something like this. We have A, B, C, D, E. And we want to prove that this triangle, ABE, is congruent to triangle CBD. So this is pretty difficult to see, but let's outline it with different colors. So ABE and triangle CBD. So one of the steps in proving that these two triangles are congruent, well, first we have to find out, whether certain sides match up, certain angles match up, and you're going to be given some information. But a lot of times when you have overlapping triangles, there's information that's given in the diagram that isn't actually given to you as a statement. And we could just see it because certain things are congruent because they exist in both triangles. So it'll make a lot more sense when I just show you. So if we look at this, we see triangle ABE has this angle right here, angle B. This is an ABE. When we look at triangle CBD, we see that this angle is part of that triangle also. So because this angle is the same angle in both triangles, it's congruent to itself. So I'll just make a smaller sketch on the outside. We have this triangle ABE and this triangle CBD, but this angle is the same in both of them. So we know that the measure of angle B is congruent to the measure of angle B because it's the same. It's itself. So, and we use that, or we know that because of the reflexive property. So here, the main point is that you have information about congruence based on the diagram. Let's look at another example. So here we have a diagram, and we want to prove that triangle ABC is congruent to triangle DBC. So ABC is this triangle, and then we have DBC, which is this triangle. So examining this, we should see that they share this side. So the BC in this triangle is the same as the BC in this triangle. So BC is congruent to itself, so we know that BC is congruent to BC, and that's by the reflexive property. So without giving us information, just looking at the diagram, we have one side congruent to another side. Okay, something I want to point out that confuses some students is that we can't immediately say that angle B is congruent to angle B. Like, yeah, they both do have an angle B, but this angle is a separate angle from this angle. So just because they're both called angle B doesn't mean that they're congruent to each other. Okay, BC is in both of them, like they both have side BC, and it's the same exact side. That's how we could use a reflexive property. Okay, if we look at this one, triangle ABD, so ABD, and triangle CDB, I'm going to prove that these two are congruent. Well, again, these both share this side. This side is part of that triangle, and this side is part of this triangle. So we know that it's congruent to itself. So now be careful when you write this, in this triangle we have ABD, so we're going to call this side BD, but in this triangle we named it CDB, so instead of calling it BD, we should call it DB. This way everything aligns correctly, because angle B in this triangle eventually is going to match up with angle D in this triangle, just by looking at how it's written. So B is second, D is second. And then likewise, D in this triangle is eventually going to be proven to be the same as, or congruent to, angle B here, because this is last and this is last. So when we name the side, we should name it with how they correspond to each other. So in this triangle, B corresponds to D, so we have B, and here we have D, then we have D, then B. So going around A, B, D, so we can see it's named this way, BD, matched up with CDB, going around this way. So in this triangle, BD, in this triangle, DB. But the main point is that this side is congruent to itself. So we're given, again, a side based on a diagram. Okay, this is a little bit more advanced, but we could use a reflexive property here also. So we have triangle A, B, C, and I'm trying to prove this congruent to triangle EDF. Okay, so let's say we're given another piece of information. We're given that AF is congruent to EC. So this is AF, this little piece here. This part is congruent to this part. Okay, clearly they're not drawn congruent, but we know that AF is congruent to EC. Okay, these line segments are congruent, but this isn't a side of the triangle, and this isn't a side of this triangle. It's part of a side. So we don't even have that a side is congruent to a side at this point. But if we look at AF, it's part of this entire side, AC. If we look at EC, it's part of this entire side, FE. So we don't have that a full side is congruent to a full side of the triangle, but it's definitely a part of the side of the triangles. Okay, if we look at what's missing from this triangle, we see that FC is missing. If we look at this triangle, again we see that CF is missing. Well, FC is the same as CF, so these are congruent to each other. So in the future we're going to learn about the addition postulate and substitution, but conceptually we could make sense of this now. If FC is the same as CF, then we would know that AC is the same length as EF. And I'll demonstrate that with numbers. So if AF is 3 inches, we'll say, and EC is 3 inches, and we know that FC is, let's say, 6 inches, then we know that the length of AC is 9 inches, and the length of EF is also 9 inches. So we know that AC is congruent to EF. And that's going to work for any number. So no matter what these are going to be congruent. FC is going to be the same as CF. So they're always going to add up to be the same. So that means that the total of this AC is always going to be the same as EF. So just something else to look out for in overlapping triangles.